Hello. The title of this video, Patterns, Percolation and Pores, is to introduce the generic types of displacement process for flow in porous media, and then their implications in a qualitative fashion for displacement and recovery. So let's start by describing imbibition. So this is a process by which you've had a rock, oil has moved into the rock, or you may have air in the rock. There is also a wetting phase, which we're going to call water, that is also present in the pore space. Okay. And now what we're going to do is we're going to inject that wetting phase. So the wetting phase is going to move into the rock. And in the previous video, we talked about percolation. The wetting phase likes the solid surface. It will fill the narrowest regions of the pore space. So it will fill the narrowest throats, and it will also fill the corners and roughness of the pore space. And so you'll be filling these narrowest regions by a process that we call snap-off. And that's been described in other videos. But what about the pores, the wide regions of the pore space? This is where the movement of the wetting phase is inhibited, because the wetting phase likes the narrow regions, not the wider regions of the pore space. So what we're going to do now is we'll draw, a schematic of the pore space and how we might have different types of pore filling. The idea is as follows. You can imagine, and we'll do it just for the sake of argument like this. We can imagine what's shown shaded here is the solid, okay, and what's shown here is the pore space. And here, the way it's described is we have a pore in the center here, and we have 4 restrictions or throats. So how do we fill this pore? So the pore filling mechanisms were first described in the 1980s in a series of classic experiments and analysis by Roland Lunnemont, and they're as follows. So I do in blue. So imagine, for the sake of argument, that one of these throats, say this bottom one, it looks the narrowest, has been filled with water. So here we have this. Now, in this case, we want to fill this pore. How can the water do it? Well, the water may also fill the corners of the pore space and in 3 dimensions may be connected. But you can see here that for the water to advance through the pore is going to be quite difficult. Let's draw it. Right? The water is the wetting phase. It has a low contact angle. So we have to have a contact angle here that's less than 90 degrees. Okay, the water moves forward, that's fine. Now I inject more water from the bottom. We can imagine something like this. But in order to go across this pore space, while the contact angle is less than 90 degrees, you see that the capillary pressure, and the capillary pressure we know is sigma times the curvature. And here we actually have a capillary pressure here. The curvature is the non-wetting phase bulging into the wetting phase. The curvature is positive, but very low. The radius of curvature is large. But in order to get across, look, the water actually has to go bulge in the opposite direction. Now, water is bulging into oil or air. The curvature here is negative. So this is very unfavorable. You think, well, water is spontaneous imbibition. Water likes going into the rock. But actually here, I've got to force the water in. And in fact, the critical point comes about here, okay? When the water's moved along here, you can see the contact angle here is still measured through the water is less than 90 degrees, so it's still the wetting phase. Eventually, the water will hit here, okay, and is now able to form a new configuration, which is much more stable. You can do this, Okay, and then it can fill here, it can fill this throat, and this throat. But this process is highly unfavored. It only occurs at a negative capillary pressure. The water has to bulge into the non-wetting phase, the oil or the air. So we call this process I3, I because it's an imbibition pore filling process, and 3 because there were 3 throats that weren't full of water. And here we can see that the capillary pressure for this process is negative. It's actually very unfavored. So you might say, okay, it's very unfavored, so it's not going to happen. So what's actually going to happen? Well, it's filled this narrow throat first, right? So we get back to our original condition. We say, right, it fills this throat. But then you say, well, the next narrowest throat is here. So surely much more favorable is a snap-off process, because that happens at a positive capillary pressure. The corners, the wetting phase and the corners of the pore space swell. It's going to fill this throat next. Okay, that's fine. So instead, we're going to get an arrangement like this to begin with. Okay? Because I3 isn't going to happen. It's going to be I2. Okay, fair enough. So I2 is the process where 2 of the throats still aren't filled with water. So maybe this is going to be more positive. This is going to be more positive. That is positive capillary pressure. Let's have a look at this. Actually, this isn't too bad. We look at this and we just do it geometrically. The water can sort of do this. But now what happens? Remember, we've got to have it moving across the pore space. The critical point, sort of like this. Okay. Okay, we've moved the water across the pore space. It's always the wetting phase. It always has a contact angle close to 0. This is when the meniscus first sort of gets across the pore. Okay, and here now, immediately now the water can attach here. So we can form a meniscus like this that fills rapidly, a meniscus that fills, and we fill everything. So that's an I2 process, but the critical curvature here, the radius of curvature is huge. The curvature itself is close to 0 now. In this term, well, it's slightly positive, but it's close to 0. So here the I2 process, PC, is close to 0. So it's still not favoured compared to snap-off. Okay. Well, let's try I1. I1 is where all but one of the pores are filled with water. So this is, sorry, all but one of the throats is filled with water. So actually, this is the widest throat, isn't it? So imagine we have snap-off here, because snap-off will occur at a positive capillary pressure and looks a bit more favourable than that process. So let's have a look at this. Okay. So we actually have an initial condition like this. Now imagine the pore has a radius RP. So what's going to happen now? The water fills these 3 throats by snap-off. Okay. And then now what happens? Well, now it looks a lot more favourable. Because if we look here, right, the critical point sort of is a bit like this. And now actually the curvature increases and we can rapidly fill everything. So the critical curvature, the largest radius of curvature needed, right, before we have smaller radius of curvature and you can fill everything. So the way of thinking about it is you just draw pictures with the known contact angle and geometry. It's the one picture that has the largest radius of curvature. That's the critical one. If you can draw another picture with a smaller one, it's going to happen spontaneously. It's going to happen more readily. So slow, slow, slow as it gets to a larger radius, and then it all fills. So here, the critical curvature is around RP. So PC, now, If it's in 3 dimensions, we've got a curvature this way and this way. And in fact, you know, we need to account for the contact angle. And again, we talked about this in previous videos. PC is the order of 2 sigma cos theta over the radius of the pore. 2 because there's curvature both in this plane and in the other plane. And the cos theta is accounting for contact angle because it's not exactly a contact angle of 0. So if we look at this, these are the 3 inhibition mechanisms. There can be more if there are more throats, but basically I1's quite favored. Okay, I1 has 2 sigma cos theta over RP. I2 is not that well favored, and I3 actually is strongly disfavored. On the other hand, the other process that's occurring is snap-off, which is this sort of percolation process. And again, it's sort of outside of what I'm going to show in this video, but in snap-off, you have a curvature just in one direction, not so much in the other. So the capillary pressure for snap-off, actually filling here, PC and snap-off, is of order just sigma. There's just a 1 sigma cos theta over the radius of the throat. And actually there's another term, and again, I'm not going to derive it here, which is a contact angle dependent term. So basically snap-off is favored because you've got a throat that's smaller than the pore by definition. On the other hand, you haven't got this 2 because in fact, you've only got a really curvature in one direction. In the other direction, actually the curvature can be negative. It's actually disfavoring filling. And then you've got some contact angle dependent terms, which again begin to disfavor filling. And this actually filling, and this depends on also the angularity of the pore space. So there's a tan theta, tan alpha, where alpha is the effective angle of the pore space. So I'm not really going to dwell on this. This isn't the issue. But on the fact that there's a balance between cooperative pore filling and snap-off. And snap-off looks like it's favored because it's going in, by definition, narrow regions of the pore space, but it's not super favored because there isn't this factor of 2. So the process with the highest capillary pressure occurs, and there's also some more complex shape and contact angle dependent terms. So let's talk about, well, we talked about pores now, but what about patterns and percolation? What does this mean? So let's talk about a process to begin with where there's no snap-off. So where would you get no snap-off? You get no snap-off where there's no layer flow. So where do you not get any layer flow? Say bead packs, you can have water trapped between the beads, but those water layers aren't necessarily connected. You could have a system where in fact you start with a rock that's completely dry. So when I inject the water isn't in all of these layers. Okay? Or you can have a case actually where the contact angle is close to 90 degrees, which means that actually there isn't really any layer flow. Okay? So let's look at what that means. So imagine our sort of lattice, and we normally did it left to right. So let's do that. So here's some water. Let's fill these throats. And then we got these wider pores here to fill. Now, if it's a square lattice, coordination number 4, it's only going to fill with what? An I3 process. So that's super unfavorable. It's going to fill the smallest pore. Imagine this is the smallest pore. So it fills this pore. But now, aha, look at this pore. Once it's filled the pore, it fills the throats as well, because the throats by definition are smaller, can spontaneously fill the throats. Okay. So it fills this pore. But what about these 2 pores now? These pores can fill with I2. Now, I2 is not very favorable, but it's more favorable than I3. So in fact, it's going to fill this one and this one, this one. And then what it's going to do? Well, it's going to fill the smallest pore here, so say here, and then it's going to fill here. Now, this is interesting. You look at this. Basically fills a line of pores, then it fills the next line, then it fills the next line. There's no trapping. Basically, the water just pushes through and displaces everything. Okay? Do you see this? Well, actually, you do. You get a column of sand, dry sand, and you just have water move slowly from the bottom. It basically does that. Okay, you can see this on the beach. You can see this, you know, soaking water into a tissue. You sort of get, actually, it's not a completely flat front, but it's fairly flat, and you don't sort of leave much air or oil behind. And you can think about this, you might say, yeah, but this is regular. You know, what happens if I had a complex pore space? So imagine I've got a sort of raggedy advance of water here, okay? Like this, right? And imagine, well, where's it going to fill? And say, well, if we got the water here, right? To fill a pore here, that's a sort of I3 or whatever the coordination number is. It's very unfavored because there's just one bit of water there. Whereas what about in this dip? Well, if we've got a pore here, all the surrounding throats, apart from one, are filled. That's the whole point. It's in the dip. It's sort of almost surrounded by water, isn't it? So it's going to fill this. This is favored. So if we just have this cooperative pore filling and no snap off, we get flat frontal advance. We basically get a process where the water, the wetting phase, moves through the porous medium. And basically, although it can be random because you might say, yeah, but then this may be a really big pore, so it doesn't want to fill this, it wants to fill this because it's a small pore. Okay, there is some randomness. But you don't really get much trapping, and macroscopically, it's fairly flat. Okay, so let's look at the opposite. Let's look at a situation where we only have snap-off, so the opposite extreme. Where would we only have snap-off? Well, imagine we have a strongly wetting porous medium, okay? Strongly wetting. And in this strongly wetting porous medium, we have big pores, okay? So snap-off is always more favorable. All the throats are really, really small. Contact angle's close to zero. It's going to fill all the throats. Well, that we've already described. That's a percolation process. In fact, it's an ordinary percolation. So on our grid, what happens? We fill the smallest throat, then the next smallest, then the next smallest, then the next smallest. We're sort of doing it at random. But here's something interesting. We fill all of these throats. What about the pore? And in this case, we filled all the throats. And now the pore, filled with the non-wetting phase, is surrounded by water. Just a moment. Then it's trapped. So if we have flat frontal advance, we have basically no trapping. If we have just percolation and snap off, basically the non-wetting phase is trapped in all the pores, and the pores are where, you know, they're the wide regions with all the volume. So you basically get all trapping, right? No trapping. Basically, we can call this all trapping. So we have these two extremes. And so when we're looking at what really happens in a rock, right, and a complex rock where water is already initially present, right, we basically get a competition between pore filling and snap off. So in reality, what happens is, you know, you have some snap off because you fill the narrowest regions of the pore space. That's fine, okay? But now this is what's intriguing. Imagine here we've got a pore. So here we've got a throat we could fill by snap off. But now the pore is surrounded by water except for one throat. That's I1, that's the most favorable. So just as you think, ha, I'm going to trap you oil in this big pore because we're snapping off in all the throats, just one more to go. When there's just one more to go, it's the most favorable displacement. And that's when the water is likely, in fact, to fill the pore and yippee, the oil's escaped. Okay? So we get this competition, right, in real porous media, competition between snap off, right, just filling the narrow throats, and trapping surrounding the oil, which we described before, and what's called cooperative pore filling. So that competition determines how much is trapping. So it determines how much is trapped. So when we're looking at flow in porous media, when we're looking at flow within a rock, what are we looking at? We're looking at the competition between snap-off and cooperative pore filling. Snap-off basically snaps all the narrow regions, fills them with water, surrounds the oil can't escape. So that leads to a lot of trapping of the non-wetting phase. Cooperative pore filling, on the other hand, does the opposite. It's acting against it because it's saying, look, we don't want to fill just a pore until it's about to be surrounded by water, and then it's most favorable. So it's a competition between those two, and that determines how much trapping there is. And that is a complex, right? It depends on how well the water layers are connected. It depends on the wettability. The more wetting it is, actually, the more snap off. And it depends on the relative sizes of pores and throats. You've got these really narrow restrictions and wide regions, you get more trapping than if things are a bit more uniform, like, say, in a bead pack or a simple sandstone. Okay, that's the first point. And that determines your filling patterns. They're actually quite subtle. But now let's get the last thing I wanted to talk about in terms of patterns. This is all for an oil wet medium. But of course, once the oil's been into the pore space of the rock, you're likely to have altered wettability, mixed wet, oil wet. So let's do the last one. We're going to talk about patterns and percolation still. It's going to be quite qualitative. Look at a mixed wet, oil wet rock. Now, the initial condition here is I've injected oil into my porous medium. It's filled most of the pore space, but there'll be a few throats normally that are still full of water. So imagine these throughout the porous medium. Like this. Okay. Fair enough. Now I'm going to inject water, right, from the inlet. Like this. Okay, the water's coming in. Now, if it's more mixed wet or oil wet, what's going to happen? Well, if it's mixed wet means there's some regions of the pore space that are water wet. Water likes that. That's the process that happens first. To fill the oil wet regions of the pore space, we have to push oil in. Push water in. That's less favored. So what's going to happen if there's some mixed wettability? We maybe fill a few more of these throats, right? It's conceivable we might even fill the occasional pore if that's a water wet pore. But now the pore space is, imagine now most of the pore space is all wet. So what's going to happen? Well, it's an oil wet rock and I'm injecting water. The water is the non-wetting phase. It now becomes like a drainage process. And if it's a drainage process, actually, you want to fill the wide regions. You want to fill the pores. and you want to fill the wide throats. So you look here and you say, well, what can I do? You say, well, imagine there's a big oil wet pore here, but there's water here. So water could push through and fill a pore. Now the water can't really fill a pore in the middle of the pore space, can it? Well, it turns out, no, that's not very favoured, because the water's in the corners of the pore space. It has to come out of the corners and fill that pore. But in theory, it could do that. There is water in the corners of the pore space, but to come out of the corners requires a very negative capillary pressure. So what really happens is, when you have more oil wet regions of the pore space, you can only really fill when you've got a pore here, okay, that's next to a throat which is full of water, because now you've got a sort of reservoir of water to sort of push the oil out. Okay, that's fine. But it can also, of course, the water can also fill from the inlet, right? So the water could say there's a narrow, wide throat now, and then it always likes filling the pore. So what sort of process do we have? Because if initially there are a lot, okay, of throats and a few pores filled with water, okay? Right, let's imagine a case that's much more mixed wet. So to begin with, we've actually filled, quite a lot of throats. Well, then what's going to happen is, it's easy, right? You're just going to fill, look, I'm going to fill this pore. And I'm going to fill this pore, right? And then maybe this throat is a wide throat, and this one and this one. Now, what you can see here is, I'm now filling the wide regions of the pore space. Is the water connected? Well, technically it is, because where does the water come from? The water can flow through these layers that are, really confined in the nooks and crannies of the pore space. They're basically, when I first injected the oil, I pushed the water into the corners of the pore space. Now the solid is oil wet, so the water can't move across those, right? But it can still flow through it. So very slowly the water can flow. So it can start filling these pores. So what happens is I fill a lot of the pore space, but I'm not really connected. Okay. And what that means is that I increase the water saturation an awful lot, but the water conductance, its relative permeability, how well it flows, stays low. Now, in terms of recovery, that's actually good, because what I want is, I want to inject water. I want the water to be held in the pore space and not move, and then the oil to come out. So what you find is, in this more mixed wet behavior, this is basically a percolation process. Right? Percolation process. And it's actually good for recovery. And the reason is that I inject the water goes into the pore space, filling all the wide regions and staying there. I don't want to inject water and it just flows and gets produced again. And it's the oil that comes out. And it's a percolation process, because basically what I'm doing is I'm just filling the widest regions of the pore space. So I fill the widest pore first, then the next widest, then the next widest. I might fill a few throats. I might sort of get the connectivity going, but it's broadly speaking a percolation process. If on the other hand, it's a more oil wet rock, then to begin with, I've got very few throats that are filled with water. And anyway, the flow through these narrow layers is very slow. So yeah, okay, in theory, I might fill a few pores, but in the end, there are not many pores to fill, whereas at the inlet, I've got everything. So actually what happens is, it's much better just to fill from the inlet, and I fill the widest pores, right, that are connected to the inlet. And in fact, it's not just the widest pores, is it? Because now it's a drainage process. It fills the pores. Actually, what it's restricted by are the throats. So what happens is I inject here. I fill the widest throat. I then fill the pore, then the next widest throat, and so on. And so if it's an oil wet rock, what do I get? I get an invasion percolation process. Right. And that's exactly the same as we had before, right? If we inject oil into a water wet rock, it's invasion percolation. So if I swip everything around, I make it oil wet and inject water, that's a drainage process. Again, it's invasion percolation. So invasion percolation, however, what happens is the water goes through all the wide regions of the pore space. It finds this connected path at the critical threshold. But as I said in a previous video, in an infinite sized rock, or a large piece of rock, the saturation at which it does that is very low. So you've got some initial water saturation. You increase that initial water saturation by a small amount. The water connects through the big pores. Now, and that dominates the flow. So now the water can flow across the rock through a pathway of big pores. I inject water, it goes through those big pores, comes out again. So water goes in, out, in, out, in, out. The oil's just staying there, stuck to the surface. So this is bad for recovery. So let's just recap. We talked about snap off, basically filling the narrow regions, cooperative pore filling, which is the way in which we fill the wider pores. And cooperative pore filling is favored when it's surrounded by the wetting phase. Then we look at mixed wet rocks, where there's a wettability alteration. If it genuinely is mixed wet, what you do first is, again, in a sort of percolation process, you fill the water wet regions of the pore space. Then you start filling the oil wet regions, but you do so from the neighboring bits of water. So it's almost a percolation-like process. You can fill wide regions of the pore space throughout the rock, but you only get significant flow of water once those wide regions connect. And that's a percolation process. You have to fill a fraction of 50% or more of the pores. So what that means is that it's good for recovery in that you inject a lot of water, but the water doesn't really flow very well, but the oil does. So the phase you're trying to get out does get out. On the other hand, if it's a stronger wettability alteration, so everything becomes oil wet, you've only got a few throats throughout the porous medium that can initialize filling of the pores. And what's more, to get to those throats, you have to go through these very narrow bits of water in the corners of the pore space. So it's then much more favorable just to inject from the inlet. It's an invasion percolation process. The water is non-wetting. It doesn't like the restriction of the pore space. It goes through the widest throats, fills a pore, next widest throat fills a pore. It seems like, well, that's more difficult because it has to start from the inlet. But because it creates this exclusive connected path, it can actually get from inlet to outlet at a very low change, small change in saturation. And then it's hogged all the widest regions. So it's flowing much more rapidly. So that's actually bad for recovery. So we're going to see this in other videos. I talk about this with measured relative permeability, and I talk about this low connectivity of the the water in a mixed wet rock. And that is, it's just filling these pores throughout the pore space. And we can actually see this with three-dimensional X-ray imaging now. But this is sort of, with a blackboard, a simple qualitative explanation of why we see this and why it doesn't come as a big surprise. Okay, I'll finish there. Thank you.